Today our topic is going to be graphing, representing motion in a graph, okay? And more specifically in a position versus time graph, okay? So if we have motion that is more complex than just forward, backward, right? Sometimes we need a graph to represent that motion to help us figure out what is going on. Is it moving forward? Is it moving backward? Is it speeding up? Is it slowing down? What is happening in these position versus in these motion or these complex motion? Okay? So we've used motion diagrams before to help us show that it's going forward, it's going backward, it's going whatever. But now we're going to use an actual graph to help us do this. And it's the first one we're going to study is called a position versus time graph. We're going to look at two types of graphs. One of them is position versus time. The other one is velocity versus time. So today we're going to start with position versus time graphs. They, in a general sense, look like this, where time is on the x-axis and the object's position or displacement or whatever you want to call that is on the y-axis. Okay, so the y-axis is measured in meters. The x-axis might be measured in seconds. Okay, it's really anything that you might see it labeled in centimeters or you might see it labeled in hours. It just depends on what your object is doing, but your time and your position units can be found on that graph as well. Okay, so this is what we're going to start with, is position versus time graphs. When we show the position versus time graph, we're going to be able to find a lot of different things, okay? The first of which thing we can calculate from a position versus time graph is an object's velocity. We can figure out how fast an object is going from a position versus time graph, and we do that by calculating the slope of the line. Okay? So let's walk through this one more time. We said that the position over here, or you consider it the displacement, is measured in meters, and we said time might be measured in seconds. So let's just go back one more step here. How do I calculate the slope of a line? What's my equation for slope of a line?
Y equals mx plus b.
Okay, that's the equation for the whole line, so that's good. Y equals mx plus b. But this part of it right here is the slope. Do you remember how to calculate m? Right, so let's walk through this position of this equation for a line. This would be the y-intercept, okay? If x is equal to 0, that's y-intercept, but this is the y position. This is the slope. That's the x position. That's the y-intercept right there, okay? So the slope is what we're concerned with. Slope is calculated using the formula rise over run, okay? Or change in y over change in x. If you're unsure of that calculating slope, make sure you write out that equation. Okay, change in y over change in x. Does that sound familiar to us now that you heard it again, rise over run? Okay, what does this little delta symbol mean right here? We talked about this last time. It means change in, or it also means final minus initial. So you can also calculate slope by saying y final minus y initial over x final minus x initial, right? That's another way you could go about writing that slope equation, okay? So when I'm calculating the slope of the line, I pick any 2 points on the line. So let's go ahead and calculate the slope of this line right now. I'm going to pick any 2 points. I'm going to pick this one, and I'm going to pick the starting point, okay? Because if my starting point is 0, 0, that makes my calculation really easy. Wouldn't we agree? Okay, so let's go ahead and calculate the slope of my line here. Slope is equal to rise over run, or change in y over change in x. Sometimes your math teacher might say like y2 minus y1 over x2 minus, is that how Mr. Noll kind of teaches it, or Miss Ray or whoever it was? Okay, sometimes you'll say like that too, that's the same thing, okay? So I'm going to look at my second point. My second point has a y coordinate of 4. My first point has a y coordinate of 0. Okay, my x, which goes on the bottom, my first point has an x coordinate of 2 and 0. So I'm going to say over 2 minus 0. So that means the slope of my line is equal to 4 over 2, which is the same as 2. Does that ring a bell? Calculating slope, we feel okay about that? Now, let's look at how we know this is velocity. It tells us right here the slope of the line is equal to the object's velocity. Well, wasn't the y axis measured in meters? And isn't the x-axis measured in seconds? And to calculate our slope, we just took meters divided by seconds. That is velocity, right? Displacement divided by time is velocity. So our units here would be 2 meters per second. So if we know that the slope of our graph tells us velocity, what would it mean to us to have a negative slope? What do we know? What's it mean to have a negative slope or a negative velocity in general? It means we're moving backwards. That's exactly what's happening here. So if we look at this position versus time graph, I want to kind of walk through what's happening in this graph. Okay, here's our starting point right here. Okay, number one, this is where our graph started. It happens to be at 0. Okay, so for 2 seconds, what did this person do? From 0 to 2 seconds, what did they do?
Go backwards.
Did they? From 0 to 2 seconds, did the line move? Yep, that's okay. They just stayed still. They stayed in their starting point. From 2 to 5 seconds, what happened? They moved backwards. And now I want you to think about what happens here since it's a straight line. They moved backwards at constant speed. They moved backwards at a constant velocity. So they might have moved backward at, we can calculate the slope of this line, right? But they moved backward at a constant speed. They did not slow down. They did not speed up. Didn't speed up or slow down. They just walked at a constant speed and it happened to be in the backward direction. Okay? From 5 seconds to 7 seconds, what happened? They walked forward. So they walked in the opposite direction of where they were just walking, right? We start here, we walk backwards, and then we walked forwards. What happens at this point right here? Tell me, did anything special happen right here? He just passed his starting point again. Okay, he walked past the point where he was standing to begin. Remember, because this is position, so this is where he's at. He just walked past his starting point. Now tell me, from here to here or from here to here, which of those scenarios was he walking faster? From 2 to 5 or from 5 to 7? Which do you think he was walking faster? From 5 to 7. I would agree. He's walking faster from here to here. And how do we know that?
You can check the how far they went in the duration of time.
Yep, perfect. But the simpler answer for that is the slope is steeper. Right? I've got a steeper slope, which means I've got a greater velocity. Yes, you're exactly right. They covered more ground in less time, which means they were walking faster. But the simple way to check that is to see, was my slope really steep or was my slope really shallow? Right? A shallow slope means I'm walking pretty slow or I'm moving pretty slow. But a steep slope means I'm moving fast, okay? So tell me what happens from 7 to 12. What's happening here? He stays still. His position is not changing, which means we are standing still. It might be helpful for you to make those little notes on your graph too, right? We know that here he's standing still. Okay? From 12 to 14 seconds, here to here, what was he doing? He was walking backwards. And was he walking backwards slowly or quickly? Very quickly. Look how steep the slope is, right? Very quickly. So backwards at a constant velocity, that happens to be a fast velocity. Does that make sense? Backwards at a quick, constant velocity. Why do we know it's a constant velocity? Because it's a straight line, okay? When I say constant velocity, that would mean like I have my cruise control set, right? He's moving at the same speed the whole time he's walking backwards. All right, from 14 to 16, what's happening? Is he moving forward or moving backward? Moving forward. Here to here, he's moving forward at a constant velocity, little slower than he just was. From 16 to 18, what's happening? Standing still. Then what's he doing from here to here? Moving forward, right? We've got a positive slope. He's moving forward. And then the last second, what's he do? Standing still. And so where does he end up in comparison to where he started? In the same place. Okay, that's just coincidental. It doesn't always happen like that on graphs. You won't always see them end up in the same place that they started. But coincidentally, he did all this back and forth, walking, motion, whatever it was, and he ended up exactly where he started. Okay?
How does that work? Because
In this particular position versus time graph, did they start at the origin? Nope, they started 20 meters ahead of wherever they call the origin. Okay, that's not usually how I'll draw my graphs. I like to have them start at the origin. But in this particular graph, their starting point, wherever it was, wherever this person was walking at, was 20 meters ahead of that or above that or whatever. So what happens for the first second? They stayed still. Then what happened?
Walk forward.
They moved forward at a constant velocity. Then they stayed still. Then they
Walk backwards.
moved backwards. Okay, so what I want you to do, I want you to find the velocity. I want you to calculate the velocity from 1 second to 3 seconds. Okay, so you're going to calculate the velocity from 1 second to 3 seconds. All right, so if I want to calculate the slope of this line, my velocity is equal to 60 minus 20 over 3 minus 1. That's what I calculated for my velocity. Would you guys agree? Yeah? Could you also just see from your graph that we go up 20 over 1? That would have been an easy enough way to do it as well, right? To just see the rise over run, right? I went up 20 and over 1 second. So that would be 20 over 1. That's the same as 20 meters per second. Okay, do we feel okay about calculating the slope? Change in y over change in x. Okay, so if I would ask you to calculate the slope from 4.5 to 6 seconds, what would be different about that slope? Not only the number, but what would it come out to be? It would come out negative, and that would just tell us that we are moving backwards at that point. Okay, so let's do that one together. If I want to know the slope from 4.5 to 6 seconds, my change in y this time would be 20 minus 60 over 6 minus 4.5. So that gives me negative 40 over 1.5. I think I could do that in my head, but I'm not going to. So that gives me negative 26.7 meters per second. And so are we moving slower than 0 that we're moving negative 26? Can I move slower than 0 meters per second? Nope. So what's the negative mean? Just backwards. Just telling us direction. Okay. What if I asked you, tell me what's the object's displacement at 4 seconds? If I asked you what's the displacement at 4 seconds, what would you tell me? What's my object's displacement at 4 seconds? Yeah, you would just come read the graph. Exactly that. You would come read it and say, my displacement at 4 seconds is 60 meters. That's it. You just read where it's at on the graph. Okay? Any questions with that? We feel okay with position versus time graphs? Okay. I'm just going to give you a couple just quick questions about this one. What's my velocity during part B? What's my velocity during part B?
40? Wait, no.
I want a number. What's my velocity at B? So think through what's happening at part B. Right. I'm standing still during B, right? My position is unchanging. So if I asked you for the velocity at part B, it would just be 0 meters per second, right? I'm not moving. So I don't have any velocity, right? If I'm standing still, my velocity is 0.
Is there any way that you could have a velocity if it's staying the same? Or
If my position is not changing,
There's
that
no-
means
there's no
no velocity. Yep. Okay. In which part, A or C, do I have a larger velocity? Which part am I going faster? In part A or part C? A. And how do we know that?
not? 'Cause the slope is-
It's got a steeper slope, okay? And then at what point on the graph am I moving backwards? Tell me the time intervals in which I'll be moving backwards. What time intervals will I be moving backwards from this time to this time?
80 to 160.
From 80 to 160, right? I'm moving in the backward direction because my slope is negative, right? I'm moving backward. Do we feel pretty good about how to analyze those? Okay, I want to show you one other option for position versus time graph, which I did not put in your slides, so you might just draw these off to the side, okay? I want to show you what does a position versus time graph look like if we're speeding up or slowing down. Because until this point, all of our stuff has been constant velocity or standing still. So I want to give a couple of these examples, okay? So these are position versus time graphs. And you might want to draw them next to your other position versus time graphs. That way you have them all in one spot, but that's up to you. Okay, these are position versus time graphs where we have a speeding up or a slowing down, or otherwise an acceleration. Okay, and we're going to get to acceleration later, but I want to introduce it here with this graph. So let's say I've got a position versus time graph. This is time, this is position. And let's say my graph looks like this. It's got a curved line instead of a straight line.
Maybe it's not constant, right?
It's not constant velocity, but I want you to give me indicators like, are we moving in the positive direction or the negative direction? Are we speeding up or are we slowing down? Those are the two questions I want to answer with each of these types of graphs. So the first thing is I want you to tell me, are we moving in the positive direction or the negative direction? We're moving in the positive direction because my arrow or my graph is pointing upward. Okay, so we're moving in the positive direction. Now I want you to try to tell me, do you think we're speeding up or are we slowing down? Speeding up. I would agree. Now can you verbalize why that is the case? Bingo. It gets steeper. We start out with a really shallow slope. Here we're not going very far at each time. But as we get higher, we get farther, our slope gets increasingly steep. So we would call this speeding up in the positive direction. Speeding up in the positive direction, okay? The next type of graph I want you to see looks something like this. Okay, anytime we have a curve, we know it's speeding up or it's slowing down, okay? So let's walk through this one. What do we think first about direction? Are we moving in the positive direction or the negative direction?
Positive.
Positive direction. And tell me, do you think we're speeding up or slowing down?
Slow down.
Slowing down. Okay, because we start out with a really steep slope. And then we get to a really shallow slope. So that means we're not covering very much ground anymore. Right? We start out covering a lot of ground going really fast, and then we kind of even that out. So that's good. Slowing down in the positive direction. Okay, a couple other graphs here. Okay, what do we think that graph is representing?
They're moving backwards and then
Okay, we're going in the negative direction. And do you think you're speeding up or you're slowing down?
slowing down.
I think we're speeding up because look, we got a really shallow slope, then a really steep slope. So I think this is speeding up.
So I have a question.
Uh-huh.
So it doesn't matter which way the arrow's going, it's just if
The arrow,
It's not level.
the direction of the arrow tells us the direction,
okay, but
right?
it doesn't matter with the like with the speed. It just matters if it's like
Yeah, we're gonna look at the curve of the graph, right? That's what we're looking at.
Gotcha.
Yep. Okay, so last one, we could probably guess what the last one. Let's try it this way. If I know our last graph is going to be slowing down in the negative direction, can you tell me what the graph might look like?
It would be
Can you have an idea? Can you draw it with your hand what it's supposed to look like? A curve? What do you think? I'm slowing down in the negative direction. Is that what you guessed?
Okay, yeah.
Or not quite?
Something like that.
Slowing down in the negative direction, which means I'm going to start really steep, and then I'm going to end up in a more shallow slope. Okay?